This is the first part of Lecture 5. Lecture 5 is on wideband measurement systems. Basically, Lecture 4 was in narrowband measurement and modeling, and measurement systems for narrowband signals are not that difficult. If you remember, we modeled the narrowband signals only with a cosine, and generating a cosine is not such a difficult thing. Now, when we want to go for wideband measurements, wideband systems, we usually model the wideband systems with an impulse. And implementation of an impulse is very difficult because it has infinite spectrum. So if we go for like narrowband signaling, really truly in reality for narrowband signal, we send like a cosine, but we send a cosine which is a spectrum is like this, but in reality the spectrum of this narrowband signal is not like a cosine, it's something like this actually. Narrowband signals are something like that we approximate with this with an impulse. So this is in time, this is in frequency, and this is your like narrowband signaling. Now for wideband signaling and wideband measurements, ideally I want to send an impulse, and if I send an impulse, the spectrum is infinity. But the actual wideband systems are something like this. The spectrum is something like this. Okay? So rather than impulse, I'm sending something like a narrow pulse for narrowband communication, for wideband communication. So for wideband communication, rather than impulse, I send a narrow band, a narrow pulse. And basically, I mean, why do I do this type of like wideband channel modeling? I do it mostly for broadband communication, broadband digital communication. And in broadband digital communication, what do I do for signaling? I always send a narrow pulse. So this is a narrow pulse which is narrower than the pulses that usually I've sent, or could be the same thing, the same bandwidth. And I want to model what do I receive. So basically, I have a broadband system. I have a very narrow pulse that I'm sending for data communication. Then at the receiver, and this is the spectrum. This is the spectrum. This is the signal that I'm transmitting. At the receiver, since I have multipath, I receive several paths. And I want to know the characteristics of these paths. That's the purpose. Now, what will happen is that design of such a receiver is much more difficult than design of a cosine system. The first thing which comes to the picture is that if I had a cosine, I was only send a cosine. In here, I send a pulse and it's finished. I mean, I cannot trace it. So I have to repeat the pulse. I have to send a periodic pulse then. So the start of like wideband measurement start with sending a periodic signal, periodic pulse, very narrow periodic pulse, and just at the receiver see what will happen to different paths. So now, if I wanted to measure the received signal strength, for example, I needed only a power meter for like narrowband signaling. But in here, I need a very complete receiver which is processing the received signal. Okay, so it has a demodulator. It's just like a modem, actually a fancier modem. But when I go to narrowband, it's not even a narrowband modem. It's a very simple modem. So measurement system for narrowband is even easier than the modulation or the modem itself, but in wideband it's even more difficult than the modem. As a result, wideband measurements really was not done. And when I was talking about like classical radio channel modeling, that classical was for wideband radio channel modeling, and that one was basically developed because people couldn't measure the wideband characteristics of the channel at that time, in like 50s, 60s. They couldn't design. The first wideband channel measurement system actually was designed at Micro Corporation, the ones that I have traced, in mid-70s. They did it to measure the wideband characteristics of troposcatter channel. And it's, I think, Fontana was one of the writers. I have cited that in the book. And the paper is something like 1975, 6, something like that. So they did wideband characteristics of channel for the tropo. And then also around the same time, a little bit earlier than that, at Bell Laboratories, Don Cox also did measurements for mobile radio. Around the same time, Turin, that I mentioned earlier, at University of California, Berkeley, did some measurement techniques. Okay, all of these three people that I told you are around early 1970s for different applications. 2 of them for mobile radio, and 1 of them for troposcatter channel. Basically, the systems that they have used are time domain systems, or they are measuring the characteristics in the time domain. Means that you send an impulse and you measure the received signal strength at different delays, and then you form the delay power spectrum based on that. Okay, there are 2 techniques to do that. One is direct pulse transmission. Means that you have a pulse, you send it, and you receive what happens. The other one is using direct sequence spread spectrum and a sliding correlator. The advantage of direct sequence spread spectrum is that the ratio between peak and minimum transmitted power is very high. In pulse transmission, you send a pulse and all the power goes at one time, and then you have nothing. Then 1 strong pulse, then you have nothing. So it goes to nonlinearities of the transmitted amplifier. But direct sequence spread spectrum, as I will tell you earlier, they spread the signal over the time. Okay? As a result, you don't have any time that you're not sending anything. Power goes continually and with a fixed envelope. And fixed envelope is very important for both amplifiers. Because amplifiers, when you push them too far, they go to saturation. And for radio, you want to push them too far. So basically, there are 2 techniques: pulse transmission, direct sequence spread spectrum, using a sliding correlator. Actually, this direct sequence and sliding is a very, very important topic, and it is used in variety of, like Bluetooth looks a sliding correlator, uses a sliding correlator, for example. Every spread spectrum system uses somehow a sort of a sliding correlator. But they have other ways also to implement direct sequence spread spectrum. For measurement systems, we use a sliding correlator. A sliding correlator is a very good receiver, very good accurate receiver for spread spectrum signals, and but it's slow. It takes some time. So sliding correlators are also used in GPS systems for positioning as well. So what I do in the time domain systems, I have these 2 techniques: pulse transmission and direct sequence and sliding correlator, that I will talk about. And then frequency domain measurement system. Frequency domain measurement system, actually the first group that are reported in the literature, published, is like the work that Steve Howard did here in 1989, something like that, 1990. But that work actually was a follow-up of a work that never got published from Hewlett-Packard. In Hewlett-Packard, what they did was they were using a network analyzer to sweep the frequency domain characteristic of the channel. Very, very simple. I mean, these network analyzers, they send a cosine, they sweep the channel, and then they see that what is the frequency response, what is the received signal, then divide it together and they find the frequency response of the channel. Basically, that's what they do. And if you take the inverse Fourier transform of that, that's time domain response. People used to use other type of frequency domain measurements, but they never become that popular. In the early days, at the time that like Phil Bellow was doing his research, like in 60s, they used to send like two cosines and change the frequency of the two cosines and find a correlation of that, and based on frequency correlation function, find the other functions, like delay power spectrum. But this is different. This is very simple. That one is tough to like implement. This is very simple to implement, and also in 1990s they have FFT already embedded in the system. So you take the time response and frequency response at the same time. And also it is coherent, means it gives you the in phase and quadrature phase. So you have everything in there. It's a very, very useful technique. And as soon as Steve did that in here, many universities usually were avoiding to go into channel modeling because implementation of these real radio things are very expensive and they're very difficult. But immediately after that, a bunch of people, they threw in. One of the early groups were the group at University of Calgary in Alberta, in Canada, and they did a lot of actually indoor radio measurements around this. Then later on at Bell Labs, they started to do that. And then when people came to ultra-wideband for indoor, in which the distances are shorter, this became more and more popular. This method of like measurements of the channel characteristic, and it's because it's easy to implement. And also, the only thing that we have so far is that we synchronize the transmitter and receiver with a cable, so the distances are limited. But for indoor applications, always distances are limited anyways. So it's very well fitted. Some people at the University of Oulu, they have just changed the cable to a radio, so they are doing the same thing for longer distances. But basically in frequency domain measurement systems, what you do, you're sweeping the channel in frequency, and you find the frequency response, then you find the inverse Fourier transform, that's the impulse response. That's it. Okay. So this frequency domain measurement system, since it was like easy to implement, and also it became more popular in recent years. In standardization activities, they have a bunch of measurements. Most of that is done with like frequency domain measurement systems. And they are doing that for time of arrival measurements, for angle of arrival measurements, which is for 802.11 type of modeling, MIMO modeling, and ultra-wideband measurements for like 802.15 type of activities. And in general, for like either time domain or frequency domain measurements of the channel impulse response, always when the paths are close to one another and you cannot resolve them, they combine. You can use a spectral estimation technique to decombine them. Those type of algorithms, we refer to them as super resolution algorithms. Again, super resolution, if you remember, I told you about University of Calgary people who were following the work of the Steve Howard. Those people were one of the early people who applied these spectral estimation techniques to refine the measurements, time domain measurements. Okay, but later on, this refinement, at the beginning when they were doing the measurements of the wideband characteristics, they were interested in what? RMS, RMS delay spread. And RMS delay spread is, I mean, if your bandwidth is more than like 100 megahertz or something, like even less than that, that's like 50 megahertz or something like that, that's adequate. So if the paths are combined, they don't change the RMS as much. Then when we came to around like over year 2000, and around the year 2000, people were curious about time of arrival of the first path for geolocation application. If you want to measure time of arrival of the first path for geolocation application, now refinement of the pulses is important. So then one of my students, actually, Jinrang Li, in the literature is the first one that I know, he applied the super resolution algorithms to the measurements of frequency domain to refine the estimation of time of arrival. And that was his topic for his PhD. Earlier than him, a group at Northeastern University, they were working with one of these indoor positioning companies. They were using super resolution algorithms in time domain. That's around 1995, 1996. Brady was the professor who was doing that. And I don't remember the name of the student, but references are in the new book. So basically, this super resolution, which started in early 90s really, became more popular when positioning became more important. And in frequency domain and in time domain, it can be applied. I will give you just a general overview of that. I cannot go into the derivations because those are related to spectral estimation courses. Like in WPI, we have 534 for them. So in this lecture 5, I'm talking about time domain measurement techniques, pulse transmission, and sliding correlator direct sequence spread spectrum, and frequency domain measurement systems. Then I go over like application of frequency domain measurements in like more advanced techniques. Okay, but not much of detail in there. That's more descriptive. But the details are available in chapter 5 of the book. I mean, second edition of the book. Now, with that, let me start. So, in this first part of the lecture 5, I'm talking about time domain measurement system using pulse transmission. It's very introductory material. Basically, I have a wideband system, and I want to measure the channel impulse response. What is the channel impulse response? Channel impulse response is actually a function of tau and t. It changes in time, it changes in delay, and it's given by some variables like beta I, which is amplitude of a path, tau sub I, which is the arrival time of that path, and then phase phi of t, which is phase of that path. So associated with each path, I have an amplitude, I have a time of arrival, and I have a phase that I want to measure. And these things actually are changing in time. So I have a path in one location, its amplitude and location of arrival and phase of arrival is changing. Now, if I want to measure this, I'm in big trouble, okay? Because I need a very fast system. So what I do is that I try to do my measurement faster than variations of the channel. So in another word, I'm just considering a slow time varying channels. This is a slow time varying channels. If I have a slow time varying channel, this t goes away. Okay, so I'm measuring the impulse response of the channel before it changes. And since I cannot generate an impulse, I generate a pulse like p of t. I sense the pulse p of t, and I receive a bunch of pulses. Okay, these are those bunch of pulses. This is the delay of the first one. This is relative delay of the following paths with respect to the first path. And this tau is the propagation time, because it takes some time to go from the transmitter to receiver. And this is first path. This is the amplitude. This is the phase associated to each of the paths, because I'm interested in different paths. Now, if this P of t has very, very wide bandwidth, like ultra wide band, then I may resolve every path. Do you remember from those ray tracing things? I have many, many paths in like indoor environment. I have thousands of paths arriving. Okay, if I have like ultra wideband, I resolve a lot of them, and each path is very stable. As the bandwidth gets narrower, these neighboring paths, they combine. And when they combine, the phase is changing, they start to move up and down. Okay? But again, those movements are in the order of like FD, which is rate of variation of the channel. And rate of variation, for example, in indoor, if you remember, was like 10 hertz, around 10. Outdoor, around 100 hertz, let's say. So if I do my measurement in matter of like, for example, 100 millisecond or 10 millisecond, okay, then before channel moves, I can capture the channel. But different measurement systems, they have different time to measure. Okay. For example, the network analyzer that I told you takes like 400 nanoseconds. So how can I measure the channel? Because it changes. I mean, 10 hertz variation means that like in what? 10 hertz means that in 10 milliseconds, that's the rate of changes in time. Okay, so I cannot measure with 400 milliseconds. I cannot measure much. So how do we do the measurements? We go to an environment. We stop people from movements. We put the transmitter and receiver antenna, and we get one snapshot. Nobody moves. Okay. Then we go to another location. We do a measurement. Nobody moves. Or we design a system which is fast enough to what? To measure the channel characteristic. Now, most of my stuff are related to indoor, and the examples are related to indoor, and are the things that my students have done actually. But now other people are doing similar things, and they are becoming more popular. For example, in our case, as I told you, Ganesh was the one who did the pulse transmission for our group. He could take like 20 samples per second, which was good, twice as Doppler shift. So he could get wideband characteristics of the channel, 20 snapshots per second. He could capture the variation of the channel in wideband. But Steve's network analyzer was 400 milliseconds. He couldn't capture the variations of the channel. But then the pulse transmission technique that Ganesh had envelope detector, means that he could not detect the phase. But network analyzer could detect the phase because it has incoherent measurement. So these details makes these things different from one another. Okay. The beauty of the network analyzer, however, is that if I want to change the bandwidth, I don't need to change much of the things really, except the antenna possibly. But for pulse transmission technique, I have to change the pulse generator. But some of them are automated. But we don't have pulse generators which can generate like 1 nanosecond pulse. Pulse generators, the best that we had at that time was like 5 nanosecond pulse. This is equivalent to 200 megahertz. But if you go for like Steve's technique, you can go like 1 gigahertz bandwidth without any problem with network analyzer, which is equivalent to 1 nanosecond pulses. So frequency domain measurement system is easier to produce wideband measurements. Okay? Because if I go for pulse transmission in particular, I have to send very, very narrow pulses. And then you send very narrow, there's not much of energy in there. And the result, you cannot see it very well. But some people have done that for ultra wideband. But frequency domain for ultra wideband is much better. Certainly much better. Anyways, now let's just come back to just this part of the lecture, which is just talk about pulse transmission techniques. And then I did some of the comparisons now. I may do some comparisons at the end. Time domain measurement system. Basically, so channel is changing. We want to do the measurements before channel changes. So if it is in indoor environment, hopefully either I stop people from movement or I try to measure things like every 5 milliseconds. Okay. Now, then this is the channel impulse response. Usually in telecommunication applications, I'm interested in what RMS delay spread. I'm not interested in this, which is the fly time. So usually people normalize everything to something like this, where I have a bunch of paths. The first path is the starting point. Okay? And all the other paths, first path arrives at 0. All the others are arriving after that. Okay? And then they try to model that. One of the simple models is, what is the delay power spectrum? If this is the impulse response, magnitude square of that is the delay power spectrum for that particular location. It depends how we define the delay power spectrum. Okay, so basically this is what I'm doing. I send a very narrow pulse and I receive the receive signal. If I use an envelope detector, I miss this phase. People are not that interested in this phase. Not only measurement of this phase is very difficult, it's not very important. And always people assume that this phase is uniformly distributed. And you know why they assume uniformly distributed. Because of that Rayleigh fading stuff that I told you. But phase is always uniformly distributed randomly. So, and also this phase is changing much faster than what? Than the rest of than the amplitudes. Well, actually, they at the same rate. But phase changes very, very quickly. Okay. Now, so if we want to do the measurements, this is in time domain. Basically, we want to measure the impulse response of the channel. And in the impulse response, I want to get time of arrival of the path, magnitude of the path, most of the time. But if I have a good system, it has in phase and quadrature phase, 2 rails. Okay. Still, I have like beta and I have the tau sub I, but those are actually real and imaginary part. And by dividing them together, I can calculate the phi. Okay. Always I can take the received signal multiplied with a cosine and a sine to get the in phase and quadrature phase. In phase, quadrature phase are real and imaginary part of the received signal. And based on that, I can calculate the phase. But I don't measure the phase like directly. And that's okay. So now, to measure the impulse response, as I told you earlier, I have 2 techniques: direct pulse transmission and direct sequence and a sliding correlator. I'm talking about pulse transmission in this part of the lecture, which is the simplest one. In pulse transmission, basically this is what I'm doing. I'm sending a very narrow pulse. In Ganesh's case, for example, he was sending like a pulse which was 5 nanosecond width. And he takes that pulse and he modulates it, and then you send it at the receiver, you demodulate that, and put it on the scope. Now, since this pulse is sent like periodically, if you look at the scope, you see this thing. These are different paths. And this is your channel profile. Now, when you want to design this thing, you want to design it so that the width of this pulse is much smaller than multipath spread. See, you have like an impulse response, which is something like this. I mean, typical impulse response in an area. You have something like, if you remember, this is the general impulse response. From here to here is your tau sub m, which I call it like maximum delay spread. This is the max delay spread. Delay spread. This is what you want to measure. This thing is what you want to measure. Okay. If you want to measure, you're also forced to send the pulse periodic. So this distance from here to here, or from here to here, which is, I call it TS, should be greater than this tau sub m. That's one criteria. Otherwise, these pulses overlap. Okay, so on the scope, you don't see the impulse response. You see the earliest version of the impulse response. So that's one condition. The other condition is that if my bandwidth is not, or my pulses are not narrow enough, my pulses are too big, I'm combining too many of these paths. Okay? So I want my width of the pulse, which is 1 over the bandwidth of my transmission medium, be much smaller than what? Tau of m, than this thing. Okay? And I want this period to be greater than this tau of m. These are the only two simple conditions that I have to apply to what? To my system. Okay. Now, if you want to have then if I do that, I can measure the impulse response. I can see it on the digital scope, and I can store it, and then I can analyze it in the MATLAB or whatever. Okay. Now, to have an example of this form, let's say that, this one is one example of like using 802.11. I have three things to consider so far. One is the repetition of the pulses, one is rate of variations of the channel, and one is bandwidth of the system. Okay. Now, different people do different things. Let me just give you one example in here. In indoor areas, we have seen that in chapter 3 that tau m is something like few hundred nanoseconds. Okay? So the repetition of the pulse, which is distance between these two pulses, typically people take it something like 500 nanoseconds. Okay? Then it comes for like multipath spread for this thing, for the width of this pulse. For the width of the pulse, if my purpose is generally characterize this thing, okay, then I use the maximum bandwidth that I can do. For example, for our first measurements that Ganesh did, he used 5 nanoseconds for that. Because actually it was even less than 5 nanoseconds. If it depends on you get the 3 dB or whatever. 3 dB was less than 5 nanoseconds. Okay, was like 2-3 nanoseconds. But the reason that he took it, that was the most accurate thing that we could acquire. People at Bell Lab did the same thing earlier than us, and they had like this thing around, I believe, like was more than this, like 10 nanosecond, 20 nanosecond. Ted Rappaport did something like 40 nanosecond. But all of us were doing 500 nanosecond apart for the indoor type of measurement. But based on systems that we had available, we were changing this thing. Now, however, if you have a specific application, for example, if you're just interested in like ISM bands in 2.4 gigahertz is like 84 megahertz. And for 84 megahertz, let's say at most 100 megahertz is what the width of 10 nanosecond is more than enough. So what we had with 5 nanosecond is very good, well fitted for that. But if I wanted to use this for like, this is 802.11. If I want to use it for ultra wideband, if you have like multi-carrier ultra wideband, the bandwidth is 512 megahertz. If you have the direct sequence in there, the bandwidth is something like 1.3 gigahertz. Here, the width of the pulse, this width for 500 is like what? Is like 2 nanosecond. For this one, it's like 1 nanosecond, less than 1 nanosecond. Less than 1 nanosecond. So this measurement system is not adequate for that. Okay? So this is how we select like numbers. Now what will happen if I use this 5 nanosecond that he has done for ultra wideband measurements? Well, I can apply those measurement systems for that, but it's going to combine paths. all the paths with 1 nanosecond, they are getting combined. Okay. Now, so that's one point. 2 parameters. So, width of the pulse, period of the repetition. This is how I relate them to what? To Doppler, to multipath spread. And then there is a third thing that I have to do. That's what? That's the measurement time. Okay? I'm doing these systems for indoor. Doppler shift in indoor is caused by the human body movements. And we have seen that that's like what? 10 hertz. Okay? 10 hertz, it means that if I do my Nyquist rate, which is 2 hertz of that, is 20 hertz, which means that if I do my measurements in 5 milliseconds, it's good. I can capture the variations of the channel. If my measurement system cannot do one measurement within 5 milliseconds, what I have to do is I have to stop people from movement when I do my measurement. So that's all that I need to know about what? Pulse transmission technique. So now if you want to have like a typical example, this is a very simple example on the computer, which is the one that actually Ganesh did in his measurements. Originally this was done with one of our undergraduate groups led by Tom Hoteling. He designed like this system for measurement of radio characteristics in indoor environments in like 85, 86, something like that. So basically what you have, you have like a pulse generator which is generating those narrow pulses, the one that we had, 5 nanoseconds. Then you have an oscillator. We are using like 900 megahertz or 1 gigahertz. Then you have a mixer. And then you have some attenuators and some power amplifiers. Really, this attenuator, you put it just for adjustment of the coverage, if you want. Okay. And then at the receiver, you have another set of attenuators, some preamplifiers, and then you have an envelope detector. Envelope detector is very simple. It's like a diode and RC circuit. Very simple one. So envelope detector is like a diode and an RC after that, a low pass filter. So that's one. Actually, you may not even need that, because if you put it directly to digital scope has a bandwidth of 100 megahertz. It samples the signal, and actually it acts like a demodulator. And you see the impulse response of the channel. Okay? But what you do is that the output of this thing comes to a digital scope. Digital scope is sampling that signal at very high rates. And then you can average like several cycles, and then you store that on a computer. Now, one thing that comes in here is that averaging. See, we are sending the signal like this, and it's coming repeatedly. And these digital scopes, they have bottoms that you can average. If you average, what will happen? If you average 10 times of this thing, your signal to noise ratio goes up 10 dB. Because averaging is like reducing the noise. Because signals remains the same, noise is like fluctuating. So you average more, it is like a processing gain, if you want to call it. But what is the problem with averaging? Why do you want to do averaging? When do you want to do averaging? If I'm 1 meter apart, I have a lot of signal strength. But if I go to far locations, now the signal comes low. Then I have to do averaging. But when I do the averaging now, if I do average over 10 of them, and each measurement was 5 milliseconds, 5 milliseconds times 10, I get 50 milliseconds now, so it's not good anymore. Do you follow me? So now I have to always compromise between coverage and variations. So if I go to far distances, I can average over several to bring my signal to noise ratio, but I have to stop a lot of people from movement. So I go in the weekends to do the measurements, for example. Okay, that's how we do it. Okay, so these are the parameters. I had 4 parameters that I brought to picture. One was repetition of the pulses. The other one was duration of the pulse, which is inverse of the bandwidth. One is number of averages that I do, and then is the measurement time by itself, physical measurement time, which depends on the what? Implementation of the digital scope. Digital scope is the one which is sampling these things and stores it. And it samples one of these things and stores in that particular experiment in like 5 milliseconds. Okay. Now you average it, then you will have some problem. And these are all the parameters for pulse transmission techniques. These are some sample measurements, again from Ganesh's thing. That's all of them are somewhere around, I think, in Atwater, Kent. This is like very line of sight. So the first path is very strong, and gradually these are other paths close by. This one is like close by, but direct path is blocked, so it's not the strongest path. And this one, really longer distances, and direct path is almost dying. Okay. But anyways, you do a bunch of these measurements in different locations. So you have a building you want to characterize. You go every meter, you do some measurements. And you get one of these things for like hundreds of that. And then what do you want to do? You want to analyze the tau RMS. So for each of these, you calculate one tau RMS. And then you create this CDF of this is actually complementary CDS. 1 minus CDF. CDF usually goes from 0 to 1. This one comes from 1 to 0. Okay, so it's 1 minus that. And then these are RMS delay spreads in 5 different, in fact, areas, 5 different buildings. Description of these buildings are inside your book. This is another one in 3 different areas. So what you do with these things, these are statistics of tau RMS. Then you can come and say, for example, that in this particular building, for example, I have more multipath spread. In this building, we have less. This is possibly a building which is less cluttered with walls. It's like a manufacturing floor. Possibly, this is like an office, for example, which has more walls. And then you can compare them to one another and get some conclusion. So that's one thing that you can do, and everybody does, out of like this time domain measurement. But if you want to get more curious, you want to develop model. That's a more difficult thing. Now, for the model, you need to detect all of these peaks. These are betas of i's, and then time of arrivals, which are taus of i's. And then somehow model them. Why do you want to model again? Because somebody wants to reproduce these things. Okay. Now, so that's what often in the models for multipath, we assume phase is linear, and we do the envelope detection, very simple ones. You get betas of i's and taus of i's, and we model betas of I and taus of I. So we make assumption for the phase, and we do the rest modeling, using modeling. Almost everybody does that. These are some typical, like, comparative numbers that Ganesh had derived from his measurements in like a bunch of areas. Basically, all of them are indoor areas. These are the delay spread in nanosecond. That's that taus of m that we talked about it. This is median of the RMS delay spread, and this is mean of the RMS delay spread, and this is the range of power fluctuations. So power, his power is wideband power, which is an average power, and he has up to 40 dB variations when he goes to different locations within 30 meters from the base station. and then mean of the RMS values are, the maximum is like 55 nanosecond. You remember that the maximum basic data rate is inverse of this number times 10. Okay, so if I get like 50 nanosecond, I inverse it and multiply it by 10, or maybe by 20%, for example, or 10, I'm talking about 2 megabit per second data rate. If I'm talking about this one, I'm talking about like 3 times more than that. Okay, but in general, we are not designing a system for one particular building. We design it with worst case scenario. So if I have a table like that, I get the worst case. And based on that, I discussed it. Data rate limitations or whatever. This is a measurement of wideband variations in time. And this is what Ganesh could do. He could do 20 multipart delay profiles in 1 second, which is good. And this is one sample, 20 measurements. So you're staying in one location, you put a transmitter receiver, you force people moving around, for example. And then in 1 second, while people are moving, you get 20 channel impulse responses. These are 20 channel impulse responses. And he has tried that in like line of sight and obstructed line of sight scenarios. And then he has tried to analyze what will happen in change. For example, how much RMS delay spread changes. I know how much power changes from Doppler shift, but I don't know how much RMS delay spread changes. So he does things like this in different areas. This is in time, and these are the changes in like relative multipath power. This is received signal strength. He does that for RMS as well and analyzes that. What is the good part of this? With his wideband system, when he goes from here to here, I have like variations of power which is around 4 dB, 5 dB. It's not much of variations. But you remember that in time for narrowband signal, I had like 30, 40 dB variation. What's the difference? Here, power is wideband power. What is the meaning of wideband power? I told you that earlier. Wideband power means that you take these amplitude. So these are the amplitudes. You measure, you square them and add them up without phase. Okay? Now, but if you go for narrowband, you're adding these with phasor, with random phase to one another. Okay? So when I go to like narrowband measurements, signal fluctuation is like too much, like 40 dB. When I come to wideband measurements, it's like 4 dB from his measurements, from one of his measurements. Sometimes he has more than that. One of them is here. All of them are around 4 dB actually, 4 or 5 dB channel. So signal is pretty stable. Now his bandwidth, his pulse was what? 5 nanosecond. His bandwidth is 200 megahertz. Ultra wideband bandwidth can be several gigahertz. So signal is even more stable than that. So this is one of the advantages of what? Ultra wideband that people claim. Signal doesn't fluctuate as much. Okay, it's pretty stable. Yes?
What's the PDF of these signals?
Log normal. I showed you that earlier. Yeah, the ones that I showed you, see, when you make the bandwidth wide, okay, you don't have multipath fading. So it doesn't become Rayleigh. If you remember, actually, I showed you this thing. That was a good, that was in the previous lecture, sorry. I showed you that I had some curve fitting. Those curve fitting are from these powers. And the curve fitting, they showed that you don't fit the Rayleigh distribution. You fit log normal or Weibull distribution. So if you look at the channel models then, 802.15 for example, they assume the paths are log normal. And that's the first actually standard assumes that. But if you go for GSM for example, they assume it's Rayleigh, the amplitude. The reason is that this guy has a wider bandwidth, the other guy has a narrower bandwidth. One of the early people who addressed these things with measurement is Ganesh's work actually. And they give him credit in the standardization activity, which took place like 15 years later after what he did. So it was good work, very good work, good cited. Now, this is TORMS. Pattern of TORMS is not like that. TORMS is crazy, it changes a lot, goes up and down in different, and nobody has developed any model for that. For the TORMS, what they do generally is that they come and they say, we have different buildings. Good building, bad building, average building. So TORMS in the good building is a small, average building is more than that, bad building is higher than that. We will see examples of those models in the next lecture, lecture 6. That's like typically what is done. So with that, I think I'm done with the post-transmission technique. What I did in post-transmission technique, really, the technique is very easy. But I brought the idea of what we want to measure and engineering-wise, what are the parameters which are important, and then what is the impact on like received signal strength when I have wideband, okay, which makes it log normal, and then the repetition of the pulse, what should be the distance, what should be the bandwidth, and what are the typical measurements and measurement systems. Very, very engineering oriented, like summary of post-transmission techniques. Post-transmission technique, as I said, the latest was ultra-wideband people. That they had like these narrow pulses, they were saying that its signal gets more messy, it's less controlled for modeling. Frequency domain is much more clean for modeling purposes. So for the time being, we can close this part 1 if you don't have any question. So when we come back, we start part 2, which is the sliding correlator, and I believe that will be shifted to the next week because we are already out of time. So next week when we come in, we start with part 2 of lecture 5.